Hello, my name is Gregor Miller, and today I'd like to talk to you about OpenVL, a developer-level abstraction of computer vision. I was hoping to talk about my current work at Google, but unfortunately that's not possible at the moment. So I'm presenting one of my favorite projects from working at the University of British Columbia. I think the ideas contained in the OpenVL project are insightful and can provide a new perspective on our work as researchers. OpenVL is a long-running project, started in 2008, and it took on many forms that evolved. It developed as part of an HCI project on video navigation and grew into its own platform. We worked on it with help from partners such as Avigilon, AMD, and Microsoft, and had many graduate students work on it, as well as the collaborators listed here. I'd also like to thank the organizers of CRV for having me give this presentation. I'd like to start the presentation with a survey. I'm wondering, have you ever read a paper's abstract, conclusion, and figure captions, then claimed to have read it? Have you ever put an equation in a presentation? Have you ever generated better results for the supplemental material? And have you ever written a paper review the day it was due? So if your answer to any of these is yes, you're probably an academic and quite possibly a vision expert given this conference. Survey number 2. Have you ever worried about a merge conflict? Discussed C++ over drinks? Have you ever voluntarily used Linux? And have you ever hit clean and rebuild, hoping it will work this time, fingers crossed? If your answer to any of these is yes, you can probably code. And so the intent of this talk is about developers and what they need to properly create computer vision applications. And so as computer vision researchers, we have a insight into the subtlety of how algorithms operate and the conditions under which they're going to perform well. But mainstream developers are unlikely to know those things. And so how can we provide access to computer vision to them? So as an example, this is taken from quite a slide from long ago. I'm sure the numbers have changed a lot since. But the principle is still sound. So there are many millions of CPU coders who create many millions of apps and provide good user experiences. But there's a much more niche market for things like GPU coders or computer vision coders. There's probably a lot more than 200 apps now, but there's still it's not nearly the same order that mainstream developers operate in. And so the point that Tom Malloy gave his keynote and AMD Developer Summit was trying to make was that it's really important to have good abstractions so that developers have access to those technologies, and those are the key to having those technologies adopted. And so computer vision is already quite widespread, but it can become much more accessible to mainstream developers, and we can create really compelling user experiences in new applications by providing these good abstractions. So as an example, again, this is slightly old, but the principle is still correct for this, which is that if you look at OpenCV, which is probably the most widely used vision framework, it's not aimed at mainstream developers. And so here we use face detection as an example, and if you want to, we don't consider it developer friendly for 3 reasons. One is that the algorithm used to do face detection is hard detect objects, and that's the function's name. The arguments to that function are specific to that algorithm, and there's no indication in the documentation or in the function itself of the conditions under which it operates. And this is a very common level of abstraction used for computer vision libraries, things in like MATLAB, CVT, FastCV. And so originally the idea for OpenVL came from trying to work with popular computer vision libraries to help with a video navigation and editing project we were working on. And we were having difficulties with some of the students who were working on this project. So we started exploring the space, and I was looking into how to help them. And we began talking to developers too about their experiences working with computer vision. So an example was trying to do face detection. They were very frustrated when the faces or rotated, but they're still facing the camera and they weren't being detected. And that's a failure mode inside the HAR algorithm. Obviously, modern face detection algorithms are much better, but in terms of creating something accessible to developers, the way you present the APIs or the access to algorithms is really important. And so similar for, this is an old version of FastCV, the algorithms are much more specific to the hardware, but also you really have to understand what exactly they're doing, like NCC or EMS or XU8. These are things that we don't necessarily think are accessible to developers that don't understand computer vision deeply. And we'd like to make the case for a kind of a layer, an abstraction that would provide access to these people so that they can still create powerful applications, but not necessarily need to know the details of all the algorithms. And so if you imagine there's like many millions of people, mainstream developers, and there's only, say, tens of thousands of people that really understand computer vision intimately to create really good applications. Then as a stack, you'd have something like the physical hardware. So, and then a hardware acceleration API, so you can access the hardware through software. Then a computer vision framework. So imagine this being things like OpenCV. So they have kind of core computer vision functionality. And then computer vision solutions, which will be kind of algorithms at a higher level. So things like segmentation, correspondence, a registration, applications that algorithms that have more higher level usage and are still specific to certain conditions of the problems that they create, like creating a panorama versus doing SLAM. And so we propose this computer vision problem description layer as a way to provide access to those solutions without requiring knowledge of how they work. And then applications can be based on top of this. And so each of these layers plays a role for the widespread adoption of computer vision. As an example of the users we imagine would use each of these layers, the applications are used by consumers. And we imagine the problem description would be used by mainstream developers. And then you have things like the vision solutions and the vision frameworks. They're both being used by or created by vision ninjas. And vision researchers will typically use lower level available APIs in computer vision to be able to try and create new things. To try and illustrate the idea further, we're using OpenVL. It's actually the Open Vision language. And this is used to allow us to describe what a problem is. So this means that we present the abstraction as being targeted towards mainstream developers. It's based on problem descriptions, and the description is then interpreted by the OpenVL system to select the correct algorithm or algorithms to find the required solution based on the current conditions described by the developer. So we call this an expressive interface, the what versus the how. So we describe what the task is, but not how to solve it. So as an example, using these images on the right, we have a description for face detection. So that could be that we're expecting the face to have a 3D pose, or it could be a 2D rotation. It might be expecting expressions to vary. We could be looking for different ages or occlusion, size and quantity, and potentially even species, like we really want to find cat faces or dog faces. And so OpenVL is defined using these four categories. So we have the input and the output. So for input and output, the images would be input from the developer. We then have this idea that segments are the basic unit that we use, distinct regions within the image. We then have inputs and outputs for matches and detections, representations of templates or of correspondence, and then transformations. So geometric representation like a vector of motion between segments. It could also represent perspective transformations. And we have descriptors, and these would be ways of describing well-known things like faces, eyes, hand, body. That'd be a template. we can describe the variances. So if we're doing a segmentation or a correspondence search, how do they vary across, like, say, two images? If you have two different images you're looking for correspondences, do they vary in intensity? Do they vary in texture? And then we have conditions, which are property-based requirements. Like, we're looking for segments in the image, but they have to be red. And then we can apply some constraints. So these are operation-specific hints. So like the quantity of the segments, detections, or matches we're looking for. It could be shape or regularity of segments. It could be for correspondence, a type of match. Like it could be unique, it could be one-to-many. And then we have the operations. So the operations are how we actually construct the problems that we're trying to solve. So do a segmentation, you could then do a match to find a correspondence, you could then do a solve, and the solve would use, the match would do a correspondence for the segments, and the solve would do a optimization across the matches. This might be a way of doing a registration. And so the basis for this was the segments. We wanted to create a solid basis through which to describe computer vision. Pixels are not really relevant from a higher level perspective, so we use segments and define them as a distinct, continuously bounded region within a bounded 2D plane. This was sort of analogous to triangles in graphics. This is sort of like the rasterization, real-time graphics world in OpenGL. And this was so we could remove the need to work in regular discrete space, avoid scale issues. We could allow the expression of properties such as texture, which pixels can't have, and then we'd have also image level descriptions, which could be praised to all the segments within an image, like noise, blur, detail, etc. So as an example of this, like what would it look like in code, we have a segmentation API. So here we read in the images, create our images, we add the images to OpenVL, and then we have a description of the images, so it's roughly an idea of what we expect from the images themselves, like level of noise and detail of blur. And then we create segments property, segments object, and we ask for a property of color with, and we require that the distinctiveness be high. That's what quantity high means. Those are the properties. We then provide the constraints. In this case, you can define things like the size of the quantity that you want to receive from a segmentation. Then we have a flag here called user access required, which lets OpenVL know that you want to actually use and receive the segments after you execute this operation. If you don't set that flag, then you can use other operations that will use the results of the segmentation, but they might provide further optimizations under the hood. So it's a comparison of abstraction level for the segmentation. These are 4 images that we put as input, and then we use a description. So if we say the description is using color, I want high distinctiveness, this would be one example of a result for each of the images. If we say the description of property of color, we want a medium distinctiveness, we want a regular shape and small size, then we get a result like this. If we tell it the property should be intensity with high distinctiveness, we get these results. And if we use texture, medium distinctiveness, and then provide a measure of the texture, in this case the wavelength, then we can get examples back of results on these images. So what's happening is you can see the segmentation, first of all, is image dependent. So the quality of the result really does depend on the input image. Sometimes a color high distinctness does not work well for the bowl, but the texture worked very well in comparison. So it's important to choose the correct method for the current conditions. And so if we can describe those conditions correctly for the image that we have, then we can provide a much more effective result for the user. And so the way it works is OpenVL actually takes in these descriptions and it maps a description to the algorithm or algorithms, and then it derives the parameters necessary based on those properties. So these are the algorithms that were chosen by OpenVL based on those descriptions. Another example is in correspondence. So if if you're using OpenCV to register images, you typically select your feature type and create features, choose matching, select optimization. In OpenVL, what you do is provide information on the image, like the level of detail, noise, etc. Describe the variances between them. So it could be the intensity, it could be saturation, it could be the tilt distortion between the positions of the viewpoints. And then you choose the transform type you're looking for, which, so in example, it could be an affine transformation. So using these images as an example, then what do we use to find the matches between these images? So there are various methods. So here's the ones that we implemented, we used OpenVL, sorry. But they're not exposed by OpenVL. So you effectively describe what your problem is, and OpenVL will pick the ones that correspond to that description. So, for example, we had to run experiments to work out, is SIFT better than the SURF for the change in angle? Is HOG better than BRIEF for intensity changes? Is BRIEF better than SIFT for more efficient computation? Because they're not always documented. Like the papers will talk about their performance and relate to others, but not in terms of like if they use these 6 descriptors and how you find the detection of the features and then compute the descriptors. Not a lot of work done on this. So we did a study across these things using synthetic data to work out which ones would perform best in different circumstances. Once we did that, we were able to encode that knowledge of the performance into OpenVL abstraction. And this is something that really screams out for a machine learning approach. But the principle we were trying to demonstrate with this was that you can do a better job of things like correspondence for a user that doesn't really know what they're supposed to be doing by letting them describe it in higher level terms. And it will allow an effective result to be chosen. The final example I wanted to go through was articulated human pose detection. And so we developed a task-based description for pose detection algorithms, which involved identifying the conditions of the problem. So we looked at things like regular pose, which could be, you're expecting all limbs to be visible, and they're not. They're taking up say some percentage of the frame. Might be that the lower body is occluded. You might have a scene with high clutter. It might be that the body actually takes up a lot of the original image. And there could be some occlusion present. And so we had to take 5 different algorithms, and we tried to map them by looking at the conditions that they work in. Some of these were easy because some of the algorithms, they only work on, say, upper body detection. Others are more difficult to determine, so I had to run tests on things like the pose type they could work on, the presence of clutter, how much occlusion could be present. And so as a quick example of what we did to evaluate this, we defined a description for 50 images. We then executed all algorithms on all the images. We had OpenVL select an algorithm. This was essentially, OpenVL selection was based on a evaluation by us as researchers on how well each algorithm roughly performs based on our observations. And so OpenVL kind of encoded the expert knowledge in this case. The method with the best result was determined qualitatively from the each image for the 5 algorithms, and we would then check to see which method OpenVL chose. For a success rate, we got 76% for the optimal result and 91% for an acceptable result. So essentially, the 91% of cases it chose the optimal or the second best algorithm. So moving on, the kind of last thing that I think is interesting and important about using an abstraction like this is it gives you access to providing an abstraction across a CPU implementation, a GPU implementation, mobile, cloud implementations. As an example, I implemented the segmentation part of OpenVL entirely on a GPU. Not on a CPU, you can use the same description and get it, but the implementation on CPU will have a different set of algorithms that are optimized for it, what it's trying to do, for what it's good at. And then for the GPU implementation, we can implement algorithms that can give you potentially higher quality or better speed, given a time budget. Mobile implementations can, be optimized for app usage, and there could be cloud implementations. You could actually just implement API locally, but have the back end just talk to the cloud and send images up there and do analysis. So this is OpenVL. The central idea of OpenVL was to have a higher level abstraction for computer vision, which is a complicated subject that is being used more and more, and especially with mobile phones and so on. It's having app developers have access to sophisticated solutions that they don't need to know how they work, but can still control them and don't have to use them as a black box directly. Can be done in a lot of cases. It could be a case of just renaming a parameter from K to regularity with documentation. The OpenVL abstraction is more heavy-handed and tries to create something that's quite unified, which is not necessarily the best approach for a lot of problems. But the idea being that you can actually create an expressive API that is usable by end users can really enhance the experience of using an API or an abstraction in anybody's products. And so it really is one of the keys to widespread adoption. And I think providing that at multiple layers, so if you're part of this stack of the GP, like the hardware, and going up to the API for the hardware, to the frameworks that are for the core functionality, to the algorithms, and then to the high level problems, they're all important, and they can all be provided in meaningful ways for the user they're targeted at. And so obviously the vision researcher doesn't want an OpenVL to use, but if they're going to create this amazing algorithm, you want it used. And so providing it through something like OpenVL or a high-level API will really make it more widespread and have technology can be adopted much more quickly. And so I'm kind of evangelizing to spread the word of trying to use this concept more often when we're designing our products, so that the end users really can benefit, and mainstream developers can benefit much more. That's my talk. Thank you very much for listening. If you have any questions, please do contact me. Thanks.